Good afternoon, everyone. We're very happy that you are still around. We don't have a whole complete empty room, so we actually have people sitting at tables and people walking in. So we're very happy to see you all. Welcome to the last talk of today. And we are going to talk about Ceph-CSI. My colleague, Madhu, and I am Niels. We're one of, or both maintainers of Ceph-CSI. Yeah, we work on Ceph-CSI for quite a while already, and any of the adjacent projects. That's it. We both work for IBM, right?
That's true.
One of the biggest sponsors of the conference. We'll speak about Ceph-CSI itself, but also about the Ceph-CSI operator and CSI add-ons. All together, they provide nice and fancy storage features, including features that are outside of the CSI specification. Ceph-CSI provides a CSI driver. The CSI specification is the container storage interface that describes a set of functions, procedures. It's a gRPC protocol, and it defines a rather simplistic view of storage. You can create volumes, delete volumes, snapshotting, and so on. It's not a very advanced protocol for storage administrators, but it's sufficient for container platforms like Kubernetes. The CSI specification defines several components. There's a controller, there is a node plugin, and the main thing that people are interested in are the volumes. This is a rather kind of abstraction. In Kubernetes, these are, for example, the volumes mapped to persistent volume claims, or actually the PVs. Persistent volume claim triggers the creation of a PV, and this PV basically is a volume in CSI speak. I won't go through all of the details that are written down. If you really want to have, obviously you can read it yourself. If you have any questions further on, feel free to ask at the end or talk to us after the presentation. So CSI and container orchestrators like Kubernetes have a little bit of different terminology, like the volumes are persistent volumes. The controller plugin is what people usually refer to as the provisioner, and the node plugin is what is called the attacher or mounter, which is run on all of the Kubernetes worker nodes. There is in Kubernetes something called the storage class, and the storage class contains some configuration details about the Ceph cluster in our case. It contains a specific set of parameters, for example, for RBD images, some of the default parameters that you would set. Do you want to have like fast diff enabled or other features? And it is sort of a template that is applied or copied for every volume that you create. Users would create in Kubernetes a persistent volume claim. This persistent volume claim contains like the size of the volume that they want, and it refers to the storage class. That's all that the user really needs to know. A storage class is an administrator managed object. Users cannot really adjust it, but users can create and delete their volume claims, which are handled by the provisioner, which uses the storage class. Ceph-CSI currently has 3 different backends, so to say. It supports CephFS, RBD, and NFS. CephFS is like a read-write-many file system, a network file system. And if you have an application that runs on different worker nodes but uses the same data, and they all need to be able to write to the data, maybe in shared directories or whatnot, then CephFS is a good choice. It functions very similar to NFS, and yeah, those are the main things. RBD is a read-write once environment. It is a local block storage, and you put the file system on top. This is what the CSI driver does for you. So usually the storage class mentions ext4 as file system to use. If you really want, you can use XFS or any of the other file systems you like. ext4 is the default. It's well tested and behaving usually quite well. Because it's a local file system, in theory, you could attach an RBD image to many worker nodes at the same time and then mount the file system, but it's a local file system. So one node writing to the file system and the other node writing to the file system or reading, they don't know about each other, and it doesn't use like cluster locking or network locking. It doesn't really work. So RBD with file system mode isn't suitable for multi-node access at the same time. However, you can use RBD in block mode for read-write many workloads, and the main workload for this is like virtual machines with live migration between nodes. One node has the virtual machine running with the volume attached, reading and writing to the disk. The virtual machine needs to migrate to somewhere else, to another node. The node is going under maintenance or whatnot. Then the RBD image gets mapped on another node in block mode. QEMU, the process running the virtual machines, knows how to prevent data corruption. It coordinates with one side and the other side before it actually switches the virtual machine over to the other side. And then, yeah, that's a read-write many workload in this case. It doesn't use a file system. It's a virtual disk image, and QEMU is in charge of keeping the data intact. We have several basic features. Obviously, the volume creation and deletion is the main thing that people use. Resizing is possible. You can expand only. And usually for backups, people want to create snapshots. Right? So you can create a new volume from an existing snapshot. It's not like rolling back a volume to a previous snapshot or so. A snapshot is a standalone object in Kubernetes, and you use it to create new volumes. So it's also ideal for building up like a testing environment with a base set of data and just clone that data to many systems if you like. Certain new features that were added to the CSI specification and implemented in Ceph-CSI as one of the first drivers is the volume group snapshot support, which is similar to consistency groups, if you want to call it in traditional storage. And changed block tracking for RBD is to provide backup vendors with incremental backups or differential backups. So you can compare two snapshots, see the difference in blocks, which blocks were modified, and the backup vendor will be able to just back up these kind of blocks. This is a very new addition. Both are relatively new to the CSI specification, and it's not widely adopted yet. We hope that other storage vendors or storage providers implement these features so that the Kubernetes community says, okay, this is something that people really want, and will adopt it. We have a few non-standard features as well. Topology-based provisioning is something that is doable in the CSI specification, but we need certain details from the Kubernetes cluster, so we actually talk to the Kubernetes cluster as a CSI driver, and that's not something that you really should do. But that's just how we were able to implement it, so it's not usable on other container platforms like HashiCorp, Nomad, or Docker Swarm. Yeah. Similar thing with encrypted volumes. We can use encryption at rest, and this also talks to some of the Kubernetes APIs directly, where users manage their encryption keys. And yes, that's just how we get the keys. So we're very unlucky that we can't provide this for any of the other platforms like Nomad. With Ceph-CSI, we also noticed that there are quite some limits in what a storage or what Kubernetes supports on storage operations. And we added a sort of extension to the CSI specification. It's a complete separate project, but there we can experiment a little bit with extra storage features. It's called CSI add-ons. And we can do volume replication, for example, setting up RBD mirroring. We can do node fencing. So if a client is misbehaving for whatever reason, we can fence off the client, or block list in Ceph speak. And because encryption is something that is not really, it's not part of the CSI specification at all, any operations that involve users interacting with the encryption, like rotating keys, these extra operations also are provided by the CSI add-ons. It's completely storage agnostic, so other vendors can implement it. And there's actually an IBM driver that I think implements the volume replication piece, but very few other drivers are involved in this. In the future, Ceph-CSI will have support for NVMe OF. So if you have an NVMe OF gateway, Ceph-CSI will be able to configure the subsystems, listeners, namespaces, and whatnot. Volume group mirroring. A volume group is not an entity that exists within Kubernetes, but in the CSI add-ons project, we added a volume group method, and volume group mirroring is possible that way as well. We have QoS for RBD, but only for RBD NBD, so the user space part, the kernel driver doesn't support QoS. And we're working on a Valero plugin to implement changed file tracking. So similar to the changed block tracking, you can have 2 snapshots of CephFS compared to each other and get a list of files that were modified. So backups don't have to back up the whole file system, but only the last pieces that were modified. And with that, we'll go to Ceph-CSI operator, and Madhu can explain a bit more about it.
Thanks, Niels. So let's start with the CSI operator. So we are set of the same maintainers who maintains the how to deploy Ceph-CSI in the Ceph-CSI repo itself using the Kubernetes templates and the Helm charts. It same goes with the Rook as well, right? We have our own templates for configuring the CSI. So it was a maintenance burden for us to have it in 2 different places, and so if there is a new feature coming in, we have to make the changes in the 2 different places. So we thought an idea that like, let's build our own operator so that everyone can consume it. So the challenging was like coming up with the CRDs, which is like kind of common for all the 3 different CSI driver, what Niels explained, like CephFS, RBD, and NFS. So, and keep on supporting the current existing deployment strategies, like using Kubernetes templates and also using Helm as well, and keep the configuration very, very minimal as much as possible. So that's how like the CSI operator came into picture, and this is how like the representation looks like. We have 4 different custom resources for the CSI operator. The one is the operator config. This is a high-level configuration. It's per operator. Basically, this contains the configuration for the operator as well as the common configuration for all the CSI drivers. Because this is huge, like we don't want to repeat the configuration again and again when we set up the different CSI drivers. So if you have a look at here, like we have a spec defaults basically that is applicable for all the drivers and how we'll configure. And we have drivers. Basically, this is per CSI driver. So based on like upon your choice, you can say configure CephFS, RBD, or NFS. And this is where you can override the defaults what comes with the operator config. So if you want something to be configured, like running CSI, RBD on a different set of nodes, you can override with the driver CRs. Each driver CR will have a controller plugin and a node plugin, which is responsible for creating the volumes and mounting the volumes. This brings up the CSI driver pods. The next is like telling the CSI, this is the Ceph cluster you want to talk to create any volumes. For that, we'll have a Ceph connection CRs. This is per Ceph cluster. So you list all the monitors, which is only required for CSI to talk to the Ceph clusters. And you have client profile. This is where it gets interesting with Ceph. You have different like Rados namespace grouping, or you have some volume groups. So with standard CSI, we don't have any specification like that restricting user to have a particular namespace or a group level. So each user can create, an admin can create a different cluster ID configuration, which in turn points to a Ceph cluster. And later on, it can have like allocate sub-volume group for the specific cluster IDs. And Redis namespace for RBD as well. Then this cluster ID will be used in the storage class. That's it. Like then the users can start creating the PVCs, which will go to the respective sub-volume group or the Redis namespace. The high level, this is how it looks like when we have all this together. So I have one operator config, multiple drivers, one Ceph connection that is per Ceph cluster. If you have multiple Ceph cluster, you could create multiple Ceph connection as well. So you can create multiple profiles and point it to in the storage class. Looking at the future roadmap of the CSO operator, as this was just started very recently, but we already in the V1 phase. Basically, it's almost a matured one. So we have planned to add the support for the NVMe of CSI driver as well, so that we'll have the 4 CSI driver controlled by a single operator. And today, I think most of might have that like Kubernetes provides the sidecar for us for all this translating the kube specification into the CSI specifications. There are like almost like 5 or 6 containers what Kubernetes ships today. Now they are moving into a single sidecar, a container image, so that lot many resources will not be consumed on all the pods. So it's we also need to move to the new single sidecar model, and we'll deprecate whatever the alpha API support which we started initially, but we never broke any API from when we moved from alpha to V1 support. And we will write some migration documentation for existing users. As I mentioned earlier, like there are upstream users like who are deploying using YAMLs and the Helm charts, but we will provide a migration path for the people to move from the existing model into the new operator model. And we'll add more documentation on explaining each of the configurations so that user will be more comfortable on whatever the changes they are doing to it. Okay, next is CSI add-ons. This is kind of an enhancement what we did basically with Kubernetes. You get only the basic functionalities like creation, deletion, and snapshotting only, nothing else. So we wanted something else to support all the advanced features in Ceph. We came up with a generic solution which could be used by other storage providers as well. So this follows the same idea what the CSI specifications. You define an RPC spec basically. So you build your own client. So the storage provider just need to implement the server configurations. So we have our own controllers basically. So user just create the Kubernetes CRs. They don't know any Ceph specifications. We ship our CSI add-on controller, which understands whatever the user requests, and then it translated into the standard RPC specifications. So we will provide a CSI add-on sidecar controller, which understands the internals, and it converts into the final RPC what the storage providers implement. This is how the architecture looks like. It's one controller for the whole clusters, and we'll have a sidecar which will be running on per controller plugin or the node plugin, because we need to register. This is like the controller to the sidecar is TCP/IP communication, and sidecar to the plugin is the local socket communications. These are some of the advanced features what we have in CSI add-ons today. So one is the key rotation for the encrypted PVCs, and the network fencing, and reclaim space for the RBD volumes. We have volume. We initially started with the volume replication. So our idea was to replicate a single PVCs. Later, we came up with a group for the consistency as well, so that you could mirror a group RBD images as well. And the last one was the volume conditions. I'll talk all these things in details. Yeah, the key rotation, like this is like user will create certain CRs or with some different ways basically to rotate the keys. So as Niels mentioned, like it's like PVC to RBD image is one-to-one mapping. So we provide different ways to basically rotate the keys. The first one was like user can just annotate the persistent volumes which are encrypted and put an annotation saying, I want to rotate my keys for every week. So we take care of rotating the keys every week. And same goes for storage class level, because if you have like 1,000 of PVC, you don't want to annotate all the 1,000 PVCs. Rather, you annotate at the storage class level, then done. So we'll internally for all the PVCs created from the storage class, we'll rotate it, the keys basically, and schedule is configurable. This is how the spec looks like. So it will have all the details. The idea is pretty simple. So once the annotation is added, so internally we create a job or the cron job basically, which will target a specific persistent volume, and a schedule is weekly or it's monthly or whatever the user defines. Network fence, this was one of the important things. Like with Ceph, there are ways like you block list an IPs, right? From a Kubernetes point of view, like user doesn't know like how to execute the Ceph command. So if I want to block list any IPs or set of IPs, so we have this methodology basically. So even like user doesn't know which IP to be blocklisted as well. So we need to provide a way that this is an IP which is visible at the Ceph cluster, which need to be blocklisted. We come up with an idea of like having a network fence class which represent the Ceph connection details. The cluster is the important one. And each sidecar will create a CSI add-on node object, and in the status it will update, okay, this is the local IP which is visible at the Ceph clusters. So user will get this IP, and he creates the network fence CR. So then they could do the fencing, unfencing, and everything. This is very much useful when you have an external Ceph cluster and which is used in multiple Kubernetes clusters. So if your workload, or if the whole cluster goes down, so you have to move the workload to another cluster. At the same time, you need to ensure that if it comes back, there won't be any IO happening. So we have, and as the IPs are already preserved, so we just need to create a network fence CR. So if the cluster comes back, but you still not be able to do IO, then we could unfence it, and yeah, we'll be able to move the application to the other cluster easily. Like encryption, we have similar things for the reclaim space as well, where we will run FS stream or the RBD specify and then RBD volumes. The methods to reclaim space will remain same, like annotating as PVC or annotating the storage class, which in turn creates a reclaim space job or a cron job. A job is it's one-time operation with the targeted to a single PVC. With a cron job, it's scheduled basically and a persistent volume. And based on the schedules. Yeah. The last one is the volume replication or the volume group replication. This is where we do the mirroring operation. So as a Kubernetes user, they are not aware of the Ceph terminology. Sometimes like they don't know like what and all need to be done at the back end to establish the mirroring connections and all those things. We provided a nice APIs for them so that they could just mark the volumes as a primaries or the secondaries or do a resync operations. So with this, they are able to establish the complete RBD mirroring between the images as well. This is one of the key features for the regional disaster recovery. There are other upstream projects like Raman. It's kind of a like disaster recovery project. They use these specifications, and again, this can be storage agnostic as well. So we have tried this spec with other storage providers as well. It goes very well for them as well. So we have a concept called replication class. This is just similar to the storage class. This is at the high level. Today we support the snapshot-based mirroring. So we can configure the interval, like how frequent the snapshot has to be taken. Yeah. So the volume replication is per PVC level. So if you have a PVC, you will have a corresponding volume replication as well. And the state is the one which you will change, whether it could be a primary or the secondary. So that we will do the internal translation, and we do take care of running the RBD CLI commands to mirror the images. We initially started with this for single volumes. Then we thought like as the application keep on maturing, like their workload is spread across multiple PVCs. So they wanted some grouping concept. So then basically like when they have multiple PVCs, they just need to label those PVCs, says, okay, this is a set of PVC. We want to have a consistent replication for those things. So they will create the group replication, and most of the things will remain same, only the sector, the labels is what differs between these two things. Yeah, that is for application. And the last one is the volume condition reporter. Today with the Kubernetes, there is no way to communicate that there is something wrong once the PVCs are created. There are chances that there is some network problem. Okay, the IO is not happening. User will not come to know, okay, there is something is going on like that. There need to be a way basically to get these details back to the user so that user can see a nice representation. Okay, there is something wrong with my persistent volume claim, so I have to do something on top of it. That's where like we added this new feature. This also again on top of the existing CSS specification, which is like node get volume stats, which will report the state back whether the volume is healthy or unhealthy. From that, we'll take those details and we put an event on the PVC level saying like, okay, now the volume is healthy or unhealthy. So user just need to describe the persistent volume claim to get the details about it. And this is still in alpha state, so that's why it's not enabled by default for users. So they could enable this with an extra flags, like just annotating the CRs, the driver CR, with setting up this new feature, where this will be used basically. So once the feedback will be given to the user, they could integrate this, for example, with the rooks. So okay, if there are some problems on the node, you create a network fence CR, so blocklist that node, move the workload to the other node so that the application can easily move to the other node without any downtime. The other, it could be like generic node problem detectors. They could detect these problems, then they could create a replacement nodes as well. They can move the workloads. We could integrate with media K-test, that's another problem detector one, which could use these kind of things to solve these problems. Yeah, that's end my presentation. Any questions? Okay. Thank you.